So basically we can say that simple likelihood ratio depends on a sufficient statistic. So our testing procedures should be based on a sufficient statistic, but you have to follow all these testing procedures. You have to show that this simple ratio L theta 0 over L theta 1 less than or equal to some k, and then you have to define the testing procedure as after doing some calculations, because the value of theta 0 and theta 1 will be very important. If theta 0 greater than theta 1, you ended up with this one, but if you have the other case, you ended up with this one. Okay, so the direction of the test based on the whole procedure, so how you have to start with that, not just, okay, so I found the sufficient statistic and then write the direction of the test. Okay, so don't do that. Do the procedure and ended up with this. Okay, so let's say we have this, any other test. Okay, and we already defined the best test, let's say. Okay, best test. Okay, so then write A times the linear combination of the probability of type 2 error under the best test. So it has the minimum type size error and the maximum power, and the beta type 2 error under the best test. Okay, and we have this plus beta, b times, beta times another test. Okay, so let's do this. Let's A equals to 1 and B equals to k. Then B over A will be k. Okay, then write this alpha delta star plus k times beta delta star less than or equal to alpha delta plus k times beta delta. Okay, then write alphas in the same side of the inequality and betas in the other side. Okay, so we have this quantity, okay, and k times beta for the best test, so minimum delta case. So what is our testing procedure? We want to fix our type 1 error. So if this is like 5%, if the size of the test for both cases are the same, okay, then so the subtraction gives us 0 difference, so k times okay, and then k is just constant, so we can write this as beta delta minus star, right, beta delta star here. Okay, or in terms of powers, okay, so this will be the power function under the best test, and this is the power function under the other test. Okay, so this gives us the best test basically. Okay, so this test is the most powerful test under the null hypothesis. So this says that this delta star is the most powerful test of size alpha under H1. Okay. So I will use MPT for the most powerful test. Okay. And then our testing procedure. So MPT will be reject A0 if the simple likelihood ratio is less than or equal to, there is an equality sign, be careful about that, is less than k. So now the k is unknown, so we need to define the value of k. How we can do that? Okay, so we have to use the known information, which is alpha. At the beginning of the test, we know the size of the test, alpha. So using alpha, we need to find the probability of this rejection rule, L theta 0 over L theta 1 less than k, okay, given theta equal theta 0. Okay, and then after that, after some calculations, you will see that this probability will be y less than c, or y greater than c, where theta equal theta 0. So using the distribution of y, okay, not x, using the distribution of y, you can define the value of c. So now the c is unknown, okay. So using the distribution of y, we can define c. Okay, after finding the value of c, then we can find the power of the test, probability of type 2 error, or p-value, or whatever you want. Okay, so c is important. Actually, to be able to find p-value, we don't have to know the value of c. Okay, so sorry about that. So you don't need that information to find the p-value. Okay, so only for power and probability of type 2 error. So let's solve some questions, right? Okay, so let's start with very simple one. You already know that, actually. Normal case. You already see it in the 156 course. But let's see how we are deriving the test now. So let's say we have a normally distributed random variable with unknown mean mu and known variance sigma square. So we assume that sigma square is known. Okay, so here, and the test is given as mu equals mu 0 and mu equals mu 1. Okay, so at this point, I will not give the condition on mu 0 and mu 1, or okay, so let's keep it this way, and then later we will see if mu 0 is greater than mu 1, what happens, and when mu 0 is less than mu 1, what happens later. Okay, so let's first define the likelihood function. So first of all, we need to, let me write, construct a most powerful test, or find the most powerful test of size alpha. Okay, so in A, let's find this. Okay, so we need to find, first of all, the simple likelihood ratio. So step 1, find L, which is L mu 0 over L mu 1. Okay, L. For normal distribution, we have 2p sigma square n over 2 e to the minus summation xi minus mu 0 whole square divided by 2 sigma square 1 2 pi sigma square n over 2 e to the minus summation xi mu 1 whole square divided by 2 sigma square. So these two parts cancels out, and what we have here is e to the minus summation xi minus mu 0 whole square divide minus xi minus mu 1 whole square divide by 2 sigma square. Or when we open up the squares, parentheses. So we will have summation xi square. Okay, so let me write it. 1 over 2 sigma square parentheses, we will have summation xi square minus 2 mu 0 summation xi minus n mu 0 square minus summation xi square plus 2 mu 1 summation xi plus n mu 1 square. So we have some cancellations, as you can see. E to the minus 1 over 2 sigma square. This and this cancels out. So we have under minus 2 summation xi mu 0 minus mu 1, okay, and mu 0 square plus n mu 1 square. Okay, so I think that's enough. Then define the testing procedure. What is our testing procedure? Is reject A0 if this L, which is L theta 0 over L theta 1 less than or equal to some value k. Okay, then write the ratio at the end. I obtained that. So e to the minus 1 over 2 sigma square. Okay, and write minus 2 summation xi mu 0 minus mu 1 minus n mu 0 square minus mu 1 square, let's say, less than or equal to k. Take the ln of both sides, so we will have, so let's put minus minus and 2 cancels out, so we have summation xi mu 0 minus mu 1 divide by sigma square. Okay, so 2 cancels out, minus minus plus, and we have plus n mu 0 square minus mu 1 square divide by 2 sigma square less than or equal to ln k. Okay, so let's continue. Okay, so only statistics that we have is summation xi, as you can see. So try to keep it alone. So this quantity is just constant summation xi mu 0 minus mu 1 sigma square I from 1 to n ln k minus n mu 0 square minus mu 1 square divided by 2 sigma square. So at this point we have to be careful, because if mu 0 is greater than mu 1 we have a positive score. So when we try to keep the summation xi alone, direction of the test will not change. But if mu 1 is greater than mu 0, then we have, this will be negative, and then the range, the rejection region will be different. So let's consider two cases. If mu 0 greater than mu 1 case, and if mu 0 less than mu 1 case. So if mu 0 is greater than mu 1, then this quantity will be positive. Then summation xi less than or equal to, we have this ln k minus n times mu 0 square mu 1 square divided by 2 sigma square divided by mu 0 mu 1 over sigma square part, right? But if mu 0 is less than mu 1, this quantity will be negative. Then the change, this direction of the test will be different. So we have the same quantities, and mu 0 square minus mu 1 square divided by 2 sigma square divided by mu 0 minus mu 1 over 2, no, over sigma square, not 2. Okay, so let's say this is C, and also let's say this is C. So we can have only one condition actually, so we are considering two of them, but either this is correct or this one is correct. So let's focus on this part right now. So we try to find the value of C. So how we are doing that? We are using the known information. What we know is alpha. So alpha is given at the beginning because we need to derive the most powerful test of size alpha, right? So probability of this one will be, reject A0 when A0 is correct, when mu equals mu0. Okay, so then write in terms of this testing procedure, I'm writing capital letter because now in the probability it's a random variable, less than or equal to C, given that mu equal mu0. So now we have to define the distribution of summation xi to be able to find the value of C. Okay, so what is the distribution of C? The summation xi, then what is the value of C based on that one. So when x distributed as normal with mean mu 0 and sigma square, then summation xi distributed as normal, with mean and mu 0 and sigma square. Okay, so we can do that, or we can change it to sample mean. It doesn't matter actually. So let's keep it this way. So probability, then how we can define the value of C? Basically again using the table values. By standardizing the summation xi, then we can use the table values, then we can easily define the value of C for any normal distribution for different sample sizes, mu and sigma square values. Okay, then standardize it. Okay, so we know that this has standard normal distribution. Okay, so let's write this way, then we can easily define the value of C. So probability, standardize both sides. Okay, so I have C minus. So what is my mu now? I assume that mu 0 is correct, right? So mu is mu 0, and I have n also, divide by the standard error. Okay, that should be sigma, not sigma square, sigma square root of n. Okay, so what is the distribution of that? Is standard normal, C minus n mu 0 over sigma square root of n. So I don't have to write the given mu anymore. Okay, so now we know that this probability is alpha. It's a very small quantity. So this is for Z, so it has 0 mean. So Z is less than some given number, has very small quantity. This is like 5%, 1%, 10%, so it's very small. So Z less than or equal to some given number. So it should be in the lower side, right? So this quantity, this probability will be alpha, right? We need to define this value. So this is R, C minus n mu 0 divided by sigma square root of n. Since sigma is known, everything is easy. Okay, so in terms of standard normal table, what is this? As minus Z sub alpha, right? Okay, let me use the back side of this part. Okay, then how can we find my C? Minus Z alpha equals C and mu 0 divided by sigma square root of n. Then C will be n mu 0 minus Z sub alpha sigma square root of n. Okay, so now everything is fine. So now I found my C. So most powerful test of size alpha will be reject A0 if. Okay, so here summation xi. Now since I am using sample values, I'm writing lowercase letters, as less than or equal to n mu 0 minus Z alpha sigma over square root of n. Okay, so this will be our test. So this is the most powerful test of size alpha. So when we have a sample, this mu 0 is given from the hypothesis. So this is from the hypothesis. And alpha is known from normal table. I can find the value of C. Sigma is known. Sample size is known. So only thing that I have to know. So this is a numerical quantity. So when I take a sample, when I calculate the sum of all xi's, if this condition is satisfied, then I will reject a null hypothesis. Otherwise, I cannot reject a null hypothesis. Okay, so let's go to the other side. Okay, so this part again. So my rejection rule will be reject A0 if summation xi greater than or equal to C. So I need to find the value of C. Okay, so again using the alpha. So this is known. Probability of summation xi given is greater than or equal to C given that mu equal mu0 case. Similarly, do the standardization and given mu0. So now distribution of that is standard normal C and mu0 sigma square root of n. So I don't need to write the given part right now. So again, let's draw the normal distribution. Okay, so now this quantity equals to alpha. Alpha is again very small number, like 5%, 1%, 10%, whatever small number. So we want that our z is greater than this given quantity is alpha. Okay, so it should have a very small quantity alpha, and this quantity is represented by n mu0 sigma square root of n. So from the normal table, basically this quantity equals to z sub alpha. Okay, then z sub alpha equals c minus n mu0 divided by sigma. Then our c is defined as n mu0 now plus z sub alpha and sigma square root of n. Then our most powerful test of size alpha will be reject A0 if summation xi, right, greater than or equal to the C value and mu0 plus z sub alpha sigma square root of n. Okay, maybe in your courses you use x bar, so we can write it in terms of x bar or x bar greater than or equal to mu0 plus z sub alpha sigma over square root of n. Maybe you used to this notation, but basically they are the same. So this is how z test is derived actually. Okay, so maybe you already see the testing procedure. So what is the test statistic, and then how to write the rejection region this way. But using the most powerful test procedure, we derive the direction of the test and also find the value of the critical value. Okay, so let's say after deciding the test, so let's focus on this part, let's say. So since in this page we have that example. Okay, so the case that we have mu equal mu0 for the same distribution and mu equal mu1. And in this case, in the first case, what we had mu0 greater than mu1 case. Let's try to find the power of the test. Okay, so find the power of the test. Okay, so we already know the value of C. Okay, so you don't, after this point actually you have to write this testing procedure. Some of you in the exams keep it as C. Okay, so not write this part, summation xi less than C still, and then they cannot define the power. Okay, so we already calculated C right now. So this is our testing procedure. So what is the definition of power? Okay, so power under the alternative hypothesis. Okay, so what is that? Reject A0 when H1 is true. When H1 is true, mu equals to mu1. Okay, so rejection criteria is this one. Summation xi less than or equal to n times mu 0 minus d sub alpha. Oh, sorry, there should be, this should be in multiplication form, right? Sorry about that. This should be in multiplication. In terms of x bar, we are dividing. Okay, sigma times square root of n. Okay, where mu equals mu1. Okay, so now my mu is not mu 0 anymore. My mu is mu1. So I am saying that my x is distributed as normal with mean mu1 and variance sigma square. So sigma square is known. Okay, so now if I want to find this probability, I need to standardize it. Then I can use the standard normal tables. But how can I standardize it? Using the mu as mu1. Okay, then what is the distribution of summation xi? Normal with mean n times mu1 right now, because I assume that mu1 is correct. Okay, and n times sigma square. Based on that, I will standardize it and then write the power function. So probability that summation xi minus n mu1 divided by n sigma square root of n. Okay, then this is the constant part minus the alpha sigma square root of n.